Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 10, Organic Chemistry 3. Carbohydrates and Nucleic Acids. Cyclic structures of monosaccharides. Chemically, monosaccharides are aldehydes or ketones possessing two or more hydroxyl groups. Recall that gamma and delta hydroxyaldehyde exist predominantly as cyclic hemiacetal. If we have here gamma OH attacks on the aldehyde to form 5-member ring, we call it furanose ring, which is related to furan compound. In delta, hydroxyl group attacks the carbonyl to form 6-member ring hemiacetal called pyranose ring, related to pyrene. In many carbohydrates, both 5 and 6-member cyclic hemiacetals are possible depending on which hydroxyl group undergoes cyclization. If the OH on carbon 4 attacks the carbonyl, we get once again the furanose form. Remember, this is asymmetric, new asymmetric carbon. If the OH on carbon 5 attacks the carbonyl, we get the pyranose form, 6-member ring, and once again this carbon is asymmetric carbon. The existence of the carbohydrate in solution, for example, in aqueous solution of glucose, we find out just the only open form is 0.003% open form. The rest, 99.99, is cyclic hemiacetals. To draw the Fischer projection on the pyranose form for glucose as an example, the lone pair of oxygen on carbon 5, which we call it the configurational carbon, the OH on this carbon define if this carbohydrate is from D series or L. Now OH on the right means it's D family. Well, if it's D family and we let here attacks on this carbonyl nucleophilic addition, then we get the OH on the right, and we can get this OH on the left. If the OH is on the same direction as the OH here, then it's alpha, both on the right hand. And if it is the other way around, this is left and this is right, then it is beta. So once again, in the alpha anomer, the hemiacetal OH group is on the same side of the Fischer projection as the oxygen and the configurational carbon. What is the configurational carbon? It is the one used for specifying if we have D or L designation. Remember, these alpha and beta, we call them anomer. Anomer are two different diastereomers with different stereo configuration on carbon number 1. They are non-superimposable and non-mirror image. Why? If we have carbonyl adjacent to chiral center, the faces of this carbonyl, the upper and the bottom, are distereotopic faces. They are not enantiotopic faces. Okay? Recall this, it's very important. Now, let's apply this knowledge. The anomer alpha and beta glucopyranose should form in equal amounts because they are enantiomers. This statement is true or false? Explain your answer. Well, as we mentioned, this is false. Anomers differ in configuration at only C1. The rest of stereocenters from C2 to C5 are the same. So they are different only at C1. The configuration is different on C1. So they are diastereomers, they are not enantiomers, and since they are diastereomers, they are not going to be in equal amount. They should not form in equal amount. Okay? And in brackets, yes, the beta is 63.6%, while the D isomer 36.4%, while the open structure, as we mentioned before, it is 0.003%. Another way to draw the monosaccharides is Haworth projection. Common way to writing structure formula to represent the cyclic structure of monosaccharides with a simple three-dimensional perspective. Well, here is Fischer projection. Fischer projection here is down, and this terminal is down, and the rest of the bond up, 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 up. This is a way we transfer from the Fischer projection to dimensional, okay, three-dimensional. Now, this is not Fischer projection, this is a three-dimension, so we can rotate that, okay, 90 degree, there is no problem, keeping the stereochemistry as it is. Okay, this is in the back, and this is in the back. Okay, we would like to, the oxygen which is going to attack the carbonyl, we put it in the back, so we can rotate the three groups, HOH, CH2OH. It's allowed, right? Now, having the molecule on that form, the oxygen lone pair will attack on the carbonyl carbon to form the six-member ring. This anomeric OH, if it's down, it is alpha. If it is up, it is beta form. Now recall that we have to have the glucose molecule in that form to be able to draw Fischer projection from the beginning. The aldehyde is down, OH on carbon to right, here is left, right, right, and CH2 is down, right? That from the previous lecture. Now, for the OH on carbon 5 to attack on the carbonyl, it has to be nearby. So we have to rotate. Okay? Now the OH is nearby the aldehyde. Right? Now we have the molecule, the OH on the anomeric carbon is down, C2 is down, C3 is up, C4 is down. This is the alpha configuration, alpha D-glucopyranose. Well, the beta, the OH will be up, C2 down, up, down, and CH2 is up. Okay? This is beta. Here we have the structure of the glucose. Okay, now we would like to draw the furanose ring structure. So we are going to let this OH attack the carbonyl. So we have to rotate around it the three groups. Well, we have now the OH in the back as the aldehyde. It will attack to form the 5-member ring. If the attack causes the OH to be down, all right, it will be alpha D-glucopyranose. This is down. Carbon number 2 is down. The OH on the carbon number 3 is up, and the CH-OH-CH2 group will be up. Now, this is in the back. Concentrate with me. Now, this is a CHOOH. If the OH, I kept the conformer this way, the OH on left, the CH2OH will be in the back. Okay? So this is the alpha. And the beta, just this OH will be up. For his work on carbohydrate and vitamin C, Walter Norman Haworth obtained Nobel Prize in Chemistry in 1937. To convert Fisher projections to Haworth projections, here are the tricks. For C2, C3, C4, if the OH is on the right hand of Fisher projection, it is down in Haworth. If it is on the left hand side of Fisher, it is up in Haworth. If the sugar is D, draw the CH2 on C5 up. For D sugar, draw C1 OH pointing down for alpha and up for beta. And this is the way you should draw the pyranose ring. Well, let's apply. Here is aldose. Draw the cyclic hemiacetal forms for the aldose in Fisher and Haworth. This is aldose. So for pyranose, alpha and beta. These two are in Fisher. We would like to draw them in Haworth. This is right, so it is down. This is left, so it is up. Right, right. Down, down. This is a D, right? For D, the CH2 OH on carbon 5, it's up. For beta, OH is left, so it's up. Left, up. Right, right, down, down. And again, CH2OH is up. For furanose, so this lone pair will attack, forming a 5-member ring. OH is on this way as the OH, then it's alpha. This is right, so it is down. This is left, so it's up. Right, down. Now this group, COH this way, CH2 up, and the OH is left. For the beta, only this OH will be up, up, down, and again CHOH, CH2OH will be up, with the OH left. Draw Fisher and Haworth projections for L-glucopyranose. Here is a L-glucose mirror image to the D-glucose, OH, left, left, right, left. To transfer it to the 3-dimension, up, up. This will be in the back, and this one will be in the back. Rotate 90 degrees, will be on that structure. Remember that if we do group transformation on consequent order, we receive the same configuration about this carbon. So what I did here, I switch CH2OH with H. So H will be in the back, CH2OH will be up. And then I did switch here H with OH. So H will be up and the OH will be in the back. We did not change any configuration around any other carbons. So the OH in the back and CHO in the back attack to form the pyranose. Alpha, the OH will be on the same direction as the configurational OH. Okay, so that is left, up, then OH up, down, up, and CH2OH will be down. So that's the Fisher projection, and this is Haworth projection. Fisher projection, of course, will be here to here. If you need the alpha, the OH will be on the same direction. Now, if we have the Fisher projection for alpha D-glucopyranose, if I look for the molecule from here, then I will see the following. I will see this carbon down, this down, this OH up, this is down, and CH2OH up. We call this line and wedge form. If I look for the molecule from that side, then I will see the chair on this form. This is axial because it's down. This is down, so it is equatorial. This is up, so it is equatorial. This one is down, yes, it's equatorial. This is up, equatorial. Remember, in this chair form, the up will be equatorial, axial, 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 axial. Once again, this is down, so it is axial. Here is down, so it is equatorial. This is up, equatorial. This is down, then it is equatorial. This is up, equatorial. If we flip the chair form, then the equatorial becomes axial and vice versa. So the OH axial in here will be equatorial. That's the one down. This will down, so it will be axial. This is up, axial. This is down, axial. This is up, this is axial. Which is more stable? Of course, this one is more stable. This one is more stable because you need the substituent to be on the equatorial to be more stable. Go back to organic 1, stereochemistry. Now, if we have the beta, the OH is up. Okay? Now, if I look for the molecule from the top, then you have this up, this down, this up, this down, this is up. Again, this is a line and wedge form. What about seeing it from that way? Well, seeing it from this way, you will see the chair form. Again, this is up, so it is equatorial, equatorial, down, up, equatorial, equatorial, equatorial. That's high stable form. Axial, 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 axial. When we flip it, of course, this one will be the favored. As we see in here, the equatorial, 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 equatorial makes the beta more stable than alpha form. The beta will be 63.6, while the alpha will be 36.4 at equilibrium. So the anomer alpha and beta glucopyranose should form in equal amount because they are enantiomer. True or false? Explain your answer. Of course, we said that it's false. Anomer differ in configuration at only the anomeric carbon 1. The configuration at the remaining stereochemistry from C2 through C5 are the same. So these alpha and beta are distereoisomers, not enantiomers, and should not form in equal amount. Mutarotation and cyclic hemiacetal. Glucose crystallized from methanol has a melting point 147 degrees Celsius. When dissolved in water, it has an initial specific rotation plus 112 degree, which falls after several hours to 52.5. When glucose crystallizes from water at high temperature, above 50 degrees Celsius, it has a melting point of 150. Its initial specific rotation is plus 18.7. and rises gradually to again 52.5. The change in optical rotation is standing for what we call mutarotation. It's actually taking the molecule from the cyclic hemiacetal to open structure to another cyclic hemiacetal, alpha and beta. The alpha we can get from crystallization in methanol, while the beta we get when we crystallize from water at high temperature. And they reach equilibrium and they gave a specific rotation at plus 52. Calculate the equilibrium ratio of alpha and beta glucopyranose from the specific rotations of your anomers and observed specific rotational at mutarotational equilibrium. Well, at equilibrium we have specific rotation of plus 52.7. For pure alpha we have 112 plus. For the mole fraction we have in the media X alpha plus specific rotation of the mole fraction XB or X beta is plus 18.7. And we know that mole fraction of alpha and beta, sum of them should be 1. Solving the problem, these equations, the mole fraction of alpha will be 0.364 and the mole fraction of beta will be minus this value, so it comes up to be 0.636. At equilibrium, the equilibrium ratio of beta to alpha will be 1.75. See you next lecture.